So, good morning, everyone. I welcome you to lecture number 11 of our course, Collective Dynamics of Firms. As I mentioned in the email, today we have the course evaluation. I assume that there is not a very good statistics from 6 students here, but nevertheless, we would like to distribute these sheets. If some of you attend the exercise and haven't done this yet, and you can also do it together with Pavlin. Yeah? Maybe you can distribute this here. You return this during the break, right? I think that everyone is familiar with this, right? Or is there a question? The course number, yes, you are right. What is the course number? I write it down here. The course number is 363053. So that's the course number, yes. So you do not need to rush with this. You have time until the break. And in the meantime, I will entertain you with some slides. Right? Okay, so where are we in the course right now? We looked first into data, then we found some stylized facts about the size distribution of firms and the growth rate distribution of firms. And then for the rest of the course, we tried to develop agent-based models to reproduce the stylized fact. So the surprising finding was that you were able to reproduce these stylized facts already from very simple assumption that from the outset have not a real economic interpretation, right? If you think about the stochastic growth factors, so then it's impressive that you get the distributions without assuming anything about economics. Therefore, in the second part of the course, we try to enhance these agent-based models step by step. So the first step that we did was considering indirect competition or indirect interaction. How did we do this? We considered competition in a market, in a kind of free market capitalism. And then we found that because of the competition, some of the firms will survive and most of them not. So this is a nice intermediate result, but it doesn't reflect the state of an economy where we have small and big firms coexisting. So that means in the next step, we try to add assumptions about interaction that results in coexistence of firms. And we did this by 2 different models. One was the redistribution of wealth, which had an impact on the inequality distribution. And the other interaction assumption was cooperation by exchanging knowledge. This was done in the last course, right? So you learned how firms depend on the input of other firms. There was a baseline model, and then to this baseline model, we step by step added assumption about utility maximization. So the question now is, do we cover the economy or the dynamics of firms by just considering utility maximization? So the answer is not, as we will see today, because only in rare cases you can really calculate utilities, right? Of course, if you think of the problem from the perspective of the firm, then there is a strategic decision with whom to interact, and so on, right? But this is usually not really made based on a calculation of a utility. There are also social effects that are included in this decision. And what we do today is we entirely, in the first part, focus on the social processes. So you as a firm, you decide to do something not because you are convinced to do this, but because you observe that all others are doing it, right? So there are herding effects, there are social influences, yeah? So you observe what other big players in the market are doing, and then you try to adopt their behavior because you can observe that these are successful firms. You do not know precisely why they are so successful. You can just observe they are successful, and then you try to copy their business strategy, for example, their production layout or whatever, right? So that is the focus of today's lecture. So we will talk specifically about herding effects in firms, that firms try to imitate other firms. And we will also look into so-called lock-in effects, which means what happens if you copy the decisions of other firms or the policy of other firms. How does it lead to states that are hard to change? That's behind this path dependence and lock-in effect. So with this, we have a number of slides today. I'm not going to read all of these. I try to be a bit short. So this slide should motivate why we are interested in this. The best thing is I'm not going to talk about this famous paper by Allison and Glaser from 1997. We have put this in the literature folder. If you're interested, you can take a look into this. I just address the basic problem. If you look into the spatial distribution of firms, then you see that there are clusters of firms that emerge in certain areas. The best known example and the most copied one is the Silicon Valley, right? So there were a number of small firms that have been established either as spin-offs of Stanford University or because of some local connection with the industry. And then this started to grow and became a very prosperous area. So the question is, how did it happen? So everyone wants to have a Silicon Valley in his canton or in his country, right? So everyone wants to have this. So the question is, how did it happen? What is behind this success? And people try to understand this because if you go there and look, then you see that the firms in these local clusters have similar business culture, right? There is this saying or rumor though, that they never had written contracts. Everything was agreed on in the pub or in the coffee shop and these kind of things. Yeah? Of course, that's wrong, right? But it gives you a kind of flavor of what people think was the culture in these early days when Google was founded or Apple or something like this, right? So that's the idea. Okay. And we would like to understand how firms influence each other in creating this local culture. Because essentially, the existence of such a local culture is an important ingredient for the establishment or the survival of something like Silicon Valley. I should mention that Silicon Valley is just one example here. So we have another example in the Boston area, which is also well studied in the literature. Boston 128, that's a route out of Boston in the south where firms locate and aggregate. So, and people want to understand why is it like this. So, the modeling has to start with an agent-based framework. That means so we are not looking into density functions of how firms are distributed. We look into the problem of aggregation from the perspective of a single agent. So it is also important that we do not enforce the result, namely the emergence of a cluster and a local culture, by putting this in somehow in the model. Yeah? There are some people that are really smart in tweaking the model exactly the way they want to get the result, of course. Yeah? So here it's important to have not a central authority that basically governs the interaction behavior of this firm. Instead, it has to come up as a emerging property, as we name it in complex systems science. And the third important assumption that is listed here is we do not assume that firms get into the state based on utility calculation. Why not? First of all, we do not know the utility. We want to do it in a utility-based model, then for the rest of the lecture we just talk of how should the utility look like. And then, of course, we have to go and have to test these assumptions with an econometric model and so on and so on and so on. You know these from other courses, right? Here our assumption is, instead of explaining this from a utility maximization, we assume that firms locally influence each other. So you see what your neighbor is doing and then you behave in a similar way, or you adjust your behavior in a way that you can better collaborate with your neighboring firm and these kinds of ideas, right? So here we have listed two classes of modeling: the voter model and the bounded confidence model. So the voter model is not captured in this lecture, actually, but I should mention it. A voter model is a very simple model. You assume that an agent is characterized by one of two states, 0 or 1. This can stand for anything, right? Let's assume it's an opinion or something. And then this agent can adopt this state according to the number of other agents in the neighborhood that have the same or a different opinion or state, right? So that means the agent is in state 0, and then the agent looks around and sees he's surrounded by all firms in state 1. So, and then the probability that the agent switches towards state 1 becomes very high, or the other way around, and so on, right? So that's a voter model. First of all, it's a binary variable, -1, +1, something like this. And secondly, it's a frequency-based model. You calculate the frequency, the percentage of agents in your system, your neighborhood, and then you adjust your decision according to what all the others are doing, or different from what all the others are doing. That's also possible. Yeah? If you see everyone is in state 1, then you think it could be beneficial to be in state 0, right? And have a different business model, for example. So that's the idea. So these models, these voter models, are well studied in various scientific disciplines, notably in mathematics, but also in physics. I'm not going to talk about this. I could, because I did some work myself in this direction, but that's not important today. Maybe the important thing that you should consider is the voter is not voting, right? Yeah? So that's maybe important for you to remember, right? So no one votes here. Yeah? The voter simply adapts to what the voter sees in the environment, right? We talk about the second class of models today that's called the bounded confidence model. The difference is that the agents are characterized by a state X, but this can be a continuous variable. Let's assume it's something between 0 and 1, but it can be any value. So. And whether or not you interact with other agents depends on whether you have a similar X, whatever X is. Yeah? Let's assume X is your business model, the way you handle contracts or something like this, right? So, and then, of course, if you have a firm on the other end that has a complete different culture, complete different way of handling whatever administrative processes, then this will not work out, right? So that means the assumption is the more similar the firm is in the way it runs its business, the more easy for you it is to interact with this firm. Let us describe the baseline model first. This is a model, so we should improve maybe the literature section a bit here. So, that's a model that was first introduced in a social context. where people thought about who talks to whom, right? If you go for a party and then you talk in the first place maybe to people that are similar to you, because then you have something to share with them. Yeah? You have something to talk about. And if there are people that are not of your social level, completely different, then you have problems to interact with these people. Well, that's the assumption here, right? So that means each of these agents is characterized by a value x, and then for each possible interaction, so we choose two agents, we compare the x of I and the x of j, and we assume that they only interact if the difference is less than d in this model here, right? So that's a threshold. Of course, if the d is very large, then we end up with the so-called mean field limit, because then everyone can really interact with everyone else. But if the d is very small, then we may find a different phenomenon. Who can imagine what we will see if the d is very small, or rather small? Do you have an intuition what we will see? Yeah, how would the structure of the system look like if the d is moderately small? If the d is large, what would be the result? Everyone interacts with everyone, then because of the interaction we become very similar, right? So that means we end up with a mean culture, right? So that's a kind of mean field limit. Whereas if the d is very small, so our interaction is much restricted, yes? Yes, we have some kind of communities or clusters. So there are all these guys that have a very large X, then there are all these guys that have an intermediate X, and there are all these guys that have a small X, right? So, and those guys do not talk to each other if they belong to different groups. That's the idea. The important here is written in the lower part. This is an adaptation process. Because you interact with this other agent, you get to know the agent, and therefore your local variable, your local culture, whatever the X stands for, becomes more similar to what the other is characterized by. So you see here, so xj, for example, is the xj of the previous time step. We could add the time steps there, right, Alex? So, and so the change here depends then on the difference of the two, and the mu is a kind of convergence parameter. So if we choose 0.5 here, then it's a symmetric process. That means I change, if I'm I change my x the same way as you change your. But if it's different, then of course someone changes more. So here is some result about it. So there are a few physicists in this room. So what do you guess from this kind of dynamics here? Let us try to understand this. If you drop this part here in the beginning and you just look into the second derivative here, then it reminds you of what? Where have you seen this kind of equation before with a second derivative in space? In all diffusion equations, for example. Yeah? Every diffusion equation has a second derivative in space, right? So you know what a diffusion process is, right? Diffusion process is you start with a delta function, and then in the course of time it gets broader, broader, and broader, right? So, and then it's very broad at the end. That's the underlying process as well here, but there is a difference. The mu, because of this, so the x is bound to 1. The mu can not be larger than 1. So, and look into this factor here. So, then it means that the factor in front of this is negative. You want to talk about the difference to the diffusion process, or no? Okay. So the factor here in front is Of course, there is a rho square there and so on, but this doesn't matter, right? So we just talk about the second derivative, and then you see there's a prefactor, and this prefactor is negative. So what do we see if we have negative diffusion? We do not see this, we see this, right? So that's what you can already guess without any further knowledge about mathematics from this equation, right? In the course of time, this distribution will not broaden, but get narrower. So that is the basic meaning of this. So, or as we have put it here, if you have some initial fluctuations where some of the x are a bit more prominently represented, then this will be amplified, and other cultures that are less prominent in the initial state will die out in the course of time. So that's what you can already guess from this. So here are computer simulations that show us exactly this. So here, please have a look. You have a very broad distribution in the beginning, and then in the course of time, that's time, it becomes narrow and it converges to just one culture. Why is it like this? It's like this because the mu and the d are appropriately chosen. Do you remember what the d was? The d decides who's talking to whom, right? If I make the d smaller, as you can see in this one, then not everyone randomly chosen can talk to everyone else. And then you see, instead of one culture or one cluster emerging, you see these two clusters. Right? That's the difference. So,
why does the number of agents differ?
Excuse me?
Why does the number of agents differ?
I don't know. Oh, no idea. So, but that's something you can get with different numbers of agents as well. So, and also you remember what the mu is doing. The mu gives him somehow described the impact of this interaction, right? If the mu is very small, then we interacted, so we converged, but only very, very little. So that means my x variable changes on a very slow time scale, which on the other hand means that there are ample possibilities in between that allow me to change my direction, right? So that's something we talk about when we talk about path dependence afterwards. So this is a plot that, maybe I should go here, shows you where at the end this initial distribution converges. Here you see it converges to one state or one opinion. Here it converges to two opinions. And in this example, it converges to also discrete opinions. And you see two things here. So we assume that all of these x are possible in the beginning. So, and then you see the final distribution is characterized by these levels, right? So you have 4 different cultures. Because you have a local convergence of these guys here, they converge to that, and those guys converge to that kind of culture, right? So that's obvious. So you have 4 different levels. But what else do you see? You see that there is some overlap in these levels. Do you see this here, right? So that means if you are an agent, let's say with 0.5, initially, x equals 0.5. Then you can end up in this cluster, but you can also end up in that cluster. And this really depends on with whom you interacted initially, right? That means for those where you are part of 2 levels here, initially here, there, and there, it really depends on the sequence of interaction, with whom you talked first, who influenced your x into a particular direction, and then on the question whether or not this was amplified. I mention this because afterwards we talk about path dependence. And this is already something where it depends on the paths of your interaction. That's the meaning of path dependence, whether you end up in this local culture or in that local culture. Okay, so. Now we extend the baseline model. I hope that everyone understood what the meaning of the bounded confidence interval is. And you understood that the D is a very important parameter that somehow defines the number of levels that you can get. And you also have seen in this last slide this ambiguity for agents that can choose between that and that final state. This is the message. And now we try to understand this, to extend this. Why do we want to extend this? There's an important issue missing in this model, namely that if you got to know this other guy and have interacted with this other guy, then you should basically assume that in the next time step, you do not ignore that you had a previous interaction with this. Yeah? That's important. Yeah? Let us assume you are firm A and you will have talked to firm B in the beginning, right? About sharing some patterns or something like this, right? So, and then you talk to firm C. But talking to firm C after talking to firm B is not completely independent, because you as a firm already know what you talk to firm B, and you are influenced by this, right? And we try to capture this in a particular assumption here, which we call the in-group. The assumption here is the following. Interaction is a costly act. So you invest something, you invest your time, maybe also your money, or you disclose some of your whatever firm knowledge, or business secrets, I don't know, right? So therefore, there's some cost associated with this. And therefore, in the next time step, you will not ignore the costs you have already invested into this, which in turn means that those other firms have basically an influence on you because you talked to them before. And have, as we assumed in this model, you have somehow adjusted towards that direction. So, what we try now is that the sequence of interaction that we assume leads to a social network. I got to know you because we interacted. My X became a bit more similar to you. So therefore, you somehow influences me, and I will keep this in mind in my in-group. Yeah? And because I now add the sequence of my interaction partners to this kind of in-group, I'm no longer just dependent on my own X. I'm also dependent on the influence of those who I interacted with before, right? You see, it makes sense to think about this like this. Yeah? Is it clear what we have changed and why? We now assume that the X does not only change according to the bounded confidence model, where we become closer after interaction. It also changes because there is an influence of the past interaction partners, which are summarized in an in-group. That's the idea here. Okay, so here we formalize what I just said. So, we consider this in-group influence here in this effective value of X. So you see, the effective value of X is composed of two parts. One is my X, and the other one is the average X of the partners I have interacted with. And I can weight this influence with the parameter alpha. If I choose alpha equal 1, then I only follow the influence of the in-group partners. So that means my own opinion doesn't count anymore. And if I choose alpha equals 0, then it's the other way around. It's the original bounded confidence model. I have a sequence of random interaction, and I do not care with whom I talked before. Yeah? So these are the two different assumptions. For the alpha, we have a very mild assumption only. We say, okay, the group influence increases with the in-group size, which makes a lot of sense, right? So that's the only assumption. You can choose other assumptions here. So this is alpha is more or less proportional to I. Yeah? So it's a 1 with a little bias. Yeah? No, it's It's below 1, but with a little bias, yeah? Okay, so that's the only assumption here. And then we change the rule of the bounded confidence model a bit. We assume now that you only interact if the effective value of the x is similar. Before you looked into the x only, and now you look into the effective x. That means your x plus the in-group influence. Please.
But to get to this point,
Yeah.
we assume that the simulation has been running for some time with all the assumptions.
No, we don't assume this. We can do it in the very first step. So in the very first step, we choose each other, right? So we interact if the d, if our x is less than d. So then we change our x according to the bounded confidence interval. We become a bit more similar, and we add each other to each other's in-group. That's what we do. You consider that you have interacted with me before, and I consider that I have interacted with you before. So that means in the second round, I can no longer start with a naked x. I instead start with my x effective, right? So, which keeps the previous interaction in mind. So the next slide, in a very complicated way, just summarizes what I said here. So that's a mathematical formulation of after we interacted, I add you to my in-group, and if we didn't interact, I don't add you to my in-group. But it also says I remove you from my in-group if you were previously in the in-group. That's also important, right? So let's assume after a number of interactions with other partners, I just by chance have another interaction with you as a firm, but our x, because we had different other experience in the meantime, our x have diverged. So then why should we keep each other in the in-group? Not at all, right? So that's what this also means. I hope you understand this. So this is a removal, and that's the inclusion. Yeah. So. Now we have a kind of group effect. So we just took this example of the first interaction. I have added you to my in-group now, right? So, and then I don't interact with anyone anymore, right? Let's assume. But you interact with all these other people, right? What does it mean? It means you change your x constantly. And I, even without interacting, I'm affected by this because this interaction with the in-group has another effect on me. You understand? I do not need to interact with the other people to be affected by the group because your in-group is growing and because you are part of my in-group. Yeah? So therefore, if your x is changing, although because of your interaction with your in-group, also my x is changing. You get this point, right? So that means we have a social network that is growing here, and this social network influences us even if we are not active, because the network changes. Yeah? The network adapts. So now let's come to the results here. So that's already the result, but we have a computer simulation, and I prefer to show you this. Let me see. Okay, so that's exactly what we have just described. By the way, this video together with the paper is on our website. You can download it and you can watch it again. We just failed to include this into the notes, right? I'm sorry for this. So this is what we have described. So, at the beginning, we have a number of agents. These agents, two of these agents are randomly chosen, and then their x is compared, right? So, and if their x difference is less than d, they interact, and otherwise not. So let me. So you see the second time step, nothing happens. Why not? Because there were two agents chosen that don't interact, right? So therefore nothing happens. Third time step, nothing happened. If the agents move in this space, This has no meaning. You just look into the color of the agent. So the grayscale basically tells us about the X, right? It's from black to white. And so the link means the two of us have interacted, and at that time the X of the two of us was within this boundary. That's the idea. So now let us run, and then you see there are networks emerging from this kind of interaction. So let us run a bit. So then as I said, you should not watch the movement in space. You should better watch how the network evolves. So let us stop here at this point. So what you see is there are two components in the system. There are all these firms interacting, so which is indicated by the links. You also see that these firms have a similar gray color here, which means that the X value has become rather similar. That's no surprise. That's because they could interact and they converge to a similar one. So, and now you see these green links here actually, right? This means we are at a point in the simulation where we have chosen these two guys. If we just compare their X, Xi and Xj, there would not be any interaction possible. So, by just comparing the X. But what matters here is not the X. What matters is the X effective. That means the X plus the influence of the group, right? And because they have these groups, so basically the group influence somehow forces them to also interact or allows them to interact. Yeah? So if you think of a business model, so these guys would probably not talk to each other. But thanks to the groups they belong to, they have the ability to still talk to each other, right? Just by themselves, the CEO of company A would not talk to the CEO of company B, but because both of them belong to consortia that usually talk to each other, these guys also talk to each other. That's the idea here, right? Okay. If the green link would not exist, then these two cultures would evolve completely independently. Yeah? I hope you see this here. It's only thanks to the fact that there is the in-group. Otherwise, we are already at a point where this completely separates. So. Now, let me just continue with it. There's also then a point in time where a red link appears. I hope I see this somewhere. Yeah, it's here. So this means if I would choose these two guys at that particular moment, they would not interact anymore. So that means they have been evolved in a direction that they, even with the X effective, are not able to interact, right? So that means the group would not help them to interact. Yeah, you understand this? So they don't interact. But you see there are other links, right? And the in-group, that was the example that I tried to explain before, the in-group evolves by itself. You understand? So even if these two guys do not interact, those guys interact and other guys in these two groups interact. And this means that the in-group has its own dynamics and indirectly changes the effective X of these two agents in a way that they can converge to each other, even that they never ever interacted again after this point. You understand this, I hope, yeah? So it is thanks to the dynamics of the in-group that we see this. Okay, let me just finish with this simulation. So the nice result, or maybe we skip it here, because the nice result is already on this page. At a larger time step, we see that these two groups converge to each other, which is a very nice result because it tells us what is the role of the social network in finding a common culture in these simulations here. right? Without the social network of these firms, we would not see the emergence of a local culture. We would see instead, as you have seen in the video, the emergence of two cultures. That means the separation of the set of firms into groups that can no longer interact with each other. That's the important message here. Let me just look into one particular example here, where we try to estimate under what circumstances these talk to each other. There's another remark, Alex, so because this was copied from another talk of mine. This U threshold is somehow related to the epsilon is related to the D. I think this is never said on one of these slides, right? So now you say, well, thanks to the in-group, we all talk to each other. We will always find a local culture that we wouldn't find without the social network, right? But this is essentially not really true. If you look here into the convergence towards a local culture, that means the frequency of reaching consensus. Consensus means we are all part of one culture. So then you see that for small d, that's the epsilon, of course the probability that we end up in a local culture increases. But if the d gets larger, this probability decreases. This sounds a bit miraculous, right? Because didn't we say that the big D would allow us to interact with more people? That's true if you look into the blue curve. The blue curve is for the model without any social network and without any memory effect. So, and here you see that this is indeed increasing with the D. So, but here's another effect. Because we interacted and because our in-group is working well, we convert to a local culture very fast. Much faster than in the case without a memory, thanks to the in-group interaction. And this means that the likelihood that we can later on still talk to these guys that are on the fringe of these variable, yeah? Namely at very small, at very large x, this probability that we can still talk to them decreases very fast because we have converged in the initial state very fast. So we find a local culture, but at the same time, we lose our ability to talk to firms which have extreme opinions or extreme X. So, and therefore, this decreases afterwards. So that's the message of it. I hope you understood this. Yeah? So, of course, it's a benefit if the ability to talk to each other is very low. Yeah, then you see there is a benefit here. The red curve is above the blue curve. So for small d. But if the d is larger, then you see the fact that we speed up our convergence process and our in-groups are working well and we all talk to each other, we converge very fast, and those guys who have extreme opinions are left out of this process. So that's an interesting finding, right? Okay, so this slide gives us a bit of a motivation. I can be very fast about this. So, what do we mean by this local culture? Local culture means that we somehow follow a social norm in our business practice. There are, of course, legal contracts and written norms and rules, but there are also non-written rules. That is simply the way we trust each other, the way we behave, right? I, as company one in the Silicon Valley, will not send out emails to your employees of company B and ask them whether they want to join our company for a slightly better salary or these kind of things. You don't do this, right? So There's no legal statement that you shouldn't do this. This is what we call a local culture here, right? And this is, of course, beneficial. If you have people or firms accepting this kind of unspoken rules or social norms, it eases the process a lot in interacting between firms. That's something you understand immediately. Therefore, there is a measurable value associated with converting to a similar business practice, for example. Yeah, that's the message of this slide, basically. With this, right in time, we stop for the break of 10 minutes, and then we continue with path dependence. You can please return these sheets here, put them here on my table. Yeah? Just continue, please. So, I hope you understood from the first half of the lecture the following. First of all, there is not always utility calculation of firms. There's also social interaction. So, of course, in this particular case of the bounded confidence model, you could assume an underlying utility, right? And your utility is maximized if you interact with firms that are more similar to you, and you have less utility if you interact with firms that are more different from you, right? So this model can be mapped onto a utility maximization model. No? But in general, I want to emphasize in particular this last part where we talk existing studies focus on a game theoretical analysis. What does it mean? It means this usual prisoner's dilemma that you have in order to establish cooperation, right? You probably know this from other lectures. So I cooperate with you if you cooperate with me, but how can I know from the outset that you will cooperate with me, right? So that's a dilemma situation, and therefore, so I usually choose something where I know that my payoff is maximized, and that would be not to cooperate, because otherwise I lose my cooperation investment. Right? So that's the way this issue is usually discussed in economics. We try to choose another approach here, where we talked about these benefits in a way of influencing and changing the business practice in a way that you are better aligned and therefore get a kind of indirect utility that we are not calculating here. Right? So, but there is already one thing that I mentioned several times in the beginning. For some agent, it really depends with whom they interacted first, because this drives them either to this or to the other direction. And this is a very important scenario. The scenario where we all converge to one common culture is a very rare scenario. Basically, it only refers to mean field interaction. So that means if everyone can talk to everyone else in the system, then we have this one cluster. But the more realistic case is where we have a number of clusters. And this means that the way to how we got there is very crucial. And this is denoted as path dependence in general. So what does it mean? It means that we have small events, random events in the beginning, that during the evolution of the system, which is now the interaction scenario of the firm, get amplified in a way that at the end, the macroscopic state, that means the state of the system as a whole, depends on these random interactions that have been amplified over the curve. Yeah? So that is a very important effect. Yeah? If Mr. Hewlett has never met Mr. Packard while they were students, right? So they would not have founded a company called Hewlett Packard, right? Or these kind of things. There's a random event that led to a positive amplification, which was then reinforced over time up to the fact that we see a macroscopic state in which we have a very big company that's dominating the market, right? So this is the kind of things you should have in mind. But there are other important economic examples. One of them is about competing standards, right? You think about, so here, this is an old example, beta max versus VHS. So you probably do not know what this refers to. It refers to this video cassettes that you had when we had by the time you were born or something, right? So now we're talking about Blu-ray versus, we already forgot HD, what the other standard probably, right? So that's a similar situation. You have two competing standards in the market, and then tiny fluctuations in the beginning decide about which one will dominate. You would assume the better one, right? So that's natural. That's not true, right? If always the better one would dominate, then the world would look like completely different. So that's a very important message, actually. It is not that the better one is amplified all the time. So it is, we talk about amplification at a point where it's not clear which one is the better one, right? Okay. Let's take one example from my own work here, which just shows you results of computer simulations. So let's think about ants searching for food. So that's this example and which we simulated here. So in the middle you have the nest, and then you have 5 food sources. So here are 2, and there are 2, and there's a 5th one. So these 2, this one and this one, have approximately the same distance from the nest. So there's no advantage of either going here or going there. So the ants, by chance, found this food source earlier. And then they started to exploit this food source. So the black line that you see here, which actually is a gray line, showed the path that they use for exploiting this food source. You can think of a market, you can think of a patent or whatever, right? So, okay, so this patent was discovered first, and then everyone went into this business and tried to exploit this patent, yeah, as much as possible, yeah? Creating whatever Gorilla glasses for smartphones, or I don't know, right? So, something like this. But you see, there is a sharp turn in this path. So actually, you would have naively expected that they simply march on and detect this, right? So there was a random accident at that point that they have chosen this way. Well, once they have chosen this way, then you see they exploit all the next food source that is in the same direction, which is smart enough, right? Because so once you made it to here, so why shouldn't you take the benefit from exploiting the next market again? So, which is very close to this one. This all happens at a time where they already know these sources. Actually, they know all the sources. But the fact that they have started to build a route into this direction, this fact forced them somehow, because it was re-amplified, to first exploit this area. And only after they found out that they have exploited everything here, then they change, as you see here, their business and then go into the other area. As you can see here, that's C. And then they exploit this other area. And then at the very end, they are smart enough to leave the whole southern part of the system and then exploit this food source in the north. This was done by agents that have no representation of their environment at all, right? So, but what I want to say here is the fact that there is an early path by one ant or two ants that led them into this area. This was amplified over the course of evolution. And therefore, they first spent their time here before they went to this area. That's the message here, right? You cannot calculate the advantage of being here first. There is no advantage. That was a random event, and this was amplified. And then, of course, once you had this highway built into this area, then, of course, you use the highway, right? So you do not discard your investment. So, I mean, ants are not talking like this, but we could talk like this in a very anthropomorphic way, right? So, Okay, you do not discard your investment that you made by building this route. No, you first take what you can get from this area, right? So it's quite logic and natural. Okay. This is, as I said, called path dependence, and we try to understand now how this happens. So. The first important feature is initially there is no advantage of either of these. That's important. If there is an advantage, then of course, in particular, agents that have a bit smarter representation of the environment will certainly choose the better alternative then, of course. So, so that means equally everything is, initially everything is almost of equal value. So, but then we have a small perturbation. So you randomly choose to drive on the right side, right? And then this is amplified. Why is it amplified? Because all those people who then choose to drive on the left side, so they are eliminated from the system, right? So, therefore, you have a strong amplification effect, and at the end, everyone drives to the right side. There is not the slightest advantage of doing it. It was simply an initial symmetry break that was re-amplified. And the same, the opposite happened in countries like UK, right? And then, because these were the early business partners of Japan, when you go to Japan, everyone's driving on the left side, right? So, why that? Yeah, because they first met the people from the UK. Right? So that was basically the way how this was decided. Was not really decided, was simply amplified. Yeah? Okay. The second important ingredient of this is once everyone drives on the right side, or once everyone has bought a equipment that can read Blu-ray disc, the system gets locked into this. Because of your initial investment, you cannot simply change the whole system and say, okay, from tomorrow on, everyone is using a different standard, right? You cannot do this. Because everyone gets used to this, and it is prohibitively costly to change the state. No one is saying you cannot change the state, right? But it costs a fortune, right? It costs a fortune. And this is very important because you have reached a state at which you cannot afford to change the state anymore. The state is again and again re-amplified, right? That's a consequence of it. So, and that's called lock-in effect. Yeah? So in the previous example, you have seen already that we somehow understand how social norms emerge based on this lock-in effect. There are a few interactions in the beginning. These interactions are amplified. Other agents are involved. The system or the social network is growing. So more and more links are added to the system. And then you see that eventually some social norm emerges that was not decided initially. It is simply the result of the whole process. And once this norm has emerged, so it's a very, very difficult situation to change this again. Yeah? So. Okay, that is the rationale of what we are talking about now. So. Once the system is locked in, this has further consequences, right? So we are just talking about one dynamic process that leads us into a state that we cannot really leave anymore. But the fact that we are in that state now has consequences. And here we took examples also from the technical area. So once we all decided to have a DOS system on our computers, or once we had computers with a DOS system, then people started to write software for these systems, right? So, and we got used to these DOS, to these Microsoft products, right? And then it's even harder to leave it, no? We do not just discard the computer, we also discard everything that relates to this computer. Our whole way we process our administrative work and these kind of things. So that's a very important thing. Or the other way, once you have decided initially that you bet on the automobile, and then you create this huge highway system surrounding Los Angeles, right? Then after 50 years, you recognize that you probably had a wrong assessment of the future. But there is no way of changing this anymore, right? You can, of course, you can pay for wrecking all these highways and building whatever, railroads or something like that. Of course, in principle, you could do, but you would never get a majority for this, so people would feel affected a lot about these kind of changes. The whole suburban area is created according to the existing transportation system, and so on, and so on, and so on. You understand that this has consequences. And this means that the initial decision that you made becomes more and more reinforced on higher levels, right? You can take, if you want, you can take the whole Euro crisis and talk about this in a similar manner, right? So there were wrong decisions made in the very beginning, right? You had the time to change this. You even could afford to change it. But there were reasons to not do it. Because you didn't change it, it was re-amplified. So, and now it's amplified to a state where you can no longer change it. Right? That's the important message here. Okay, we would like to understand this in a more formal way, of course. This reminds on my core course on systems, dynamics, and complexity that I teach in the fall. Who attended this from you? Okay, most of you. It can be very good. Did you hear this before about the polar process? Yes? And we were talking about this. I thought, because how do we split material between these different courses? I can explain this to you. In systems, dynamics, and complexity, we basically look into nonlinear dynamics. Right? So, what we do here in this course, collective dynamics of firms, and we look into agent-based models. Firm A is interacting with firm B, firm A makes a decision, firm B grows, and so on. So these kind of things, we look into agents, not into the system as a whole. So macroeconomics would be that, the related part of systems dynamics. So here we look into agent-based dynamics, and therefore we have removed everything from past dependence from this course systems dynamics, because this refers to agents making decisions. Right? So therefore, it's now part of this course, and no longer part of the other one. But it's good to know, then I can be a bit more shorter. So, okay. This is a typical way of how to illustrate a positive feedback process to people that do not see the same thing from an equation. Right? So it's a graphical way of explaining it. If you have a stable process, then of course, if you have a small fluctuation here, this small fluctuation will not change the position of this ball, right? Because there is a force that brings the ball always to this state. Why? Because it's a stable state. The situation is completely different if you have an initial unstable state. Then whatever you do, the tiniest fluctuation drives you either to the left or to the right side, and then you cannot stop the system from evolving either to this or the other side, right? That's basically the equivalent. So, this is a positive feedback process here. Yeah? So that means every single deviation from the initial state is amplified, gets larger, larger, and larger. That is the idea here. So we try to model this with the so-called polar process. It's named after the mathematician George Polya, who first thought about this. So everyone is aware of this, right? Who's not aware? You are not aware.
You meant that this was taught in systems dynamics and complexity, that's why you must be aware, but it wasn't?
It wasn't, okay, yeah, that's what I said. Originally it was taught there, but then we removed it because it's basically an agent-based model. So that's the idea of Mr. Polya now. Yeah? You have an urn. So the Polya urn is just an urn, and initially You have a black and a white ball in. So. And then you add constantly balls to the system, and you choose between the black and the white balls with a probability that is proportional to what's already in the system. So let's take this initial situation, one black and one white ball. What is the probability to choose a black ball? 50%, yeah, 1/2, because there is 1/2. So now, because 50% is a random choice, you choose a black ball. So what would be this situation in the next step? You have 2 black balls and 1 white ball, right? So that means if the probability to choose the next black ball is proportional to the frequency of the black balls, and the probability that the next ball will be a black ball is, it's 2/3 versus 1/3, right? Because you have 2 black balls divided by 3 versus 1 black ball divided by 3. So, okay, and what you see is that this initial tiny fluctuation, namely to choose a black instead of white ball, is amplified over the evolution of the system. And then you end up in a situation where you can no longer handle, change the situation in the system. So we refer to this slide because that is your self-study task of this week. You should simulate this Polya process. So, using R, hopefully. So the idea here is to use a random realization. You already know how to generate random events in R. So you choose a random number between 0 and 1, and you have the following rule that's described here. You calculate at every instance in time the fraction of black and white balls in your urn, that is the small x, and then you add a black stone if the random number you have chosen is less than x, and a white stone if it's larger than x. You can invert this and can do it the other way around if you want, so it doesn't change the result. No? But what you have to remember here is that initially the x is 0.5. So to choose a random number that is above 0.5 is has the same probability than to choose a random number that's below 0.5, right? So, but then, as we described before, you add a black or white stone, and then the x is moving along this axis because you have either added a black or white stone, and that means you decrease or increase the area from which you can choose a random number, right? So let's assume the x is evolving into this direction. Then, of course, the probability of choosing a random number that is smaller than x is decreasing all the time. Why is it decreasing? Because the x is decreasing, and the x represents the fraction of the black balls in the system, right? So, and then, of course, there is nothing left, and the probability to choose a white ball is increasing all the time because this is much larger. Yeah, you got the point. So that's the result here. So from a simulation of Mr. Sturman, but you hopefully get the same thing. So you start here with at 0.5. There are 2 things that you should recognize from this picture. The first one is that these curves, there are 10 simulations here, somehow log. Yeah, so they become straight lines. And because this refers to the x, it means that the x does not change. Right? That's the first thing that you have to recognize. Do you see this? Right? So here initially there are fluctuations, but then this dumps out, and then the x is more or less stable. Why is this the case? So if time is measured in number of balls added, so then let's assume we are here, right? Proportion of black stones is about whatever, 0.005. So that means, so we have 100 if we have 100 stones here, then 5 of these stones are only black, and the other 95 are white, right? So, and now we have 200, then 10 are black, and 190 are white. And now we add a new stone, okay? So then it's not 190 divided, no, the other way around. 10 divided by 200, it's 11 divided by 201, right? So that's about the same, right? 11 divided by 201 is basically 10 divided by 10, right? So as in the whatever fifth digit after the comma, there is a little change. And that's why this gets stationary, because the system size has increased to a number where small changes like adding another ball do not matter anymore. And that's the lock-in effect. That's the first thing you have to recognize. The second thing you have to recognize is what? Who guesses? What's the second? Or what could you recognize?
First steps are most important.
That's true, yes. The first steps are most important. And then there is a third thing to recognize. The initial condition is 0.5.
Yes,
so
like the first step after the initial condition.
That's true. So that's also what Vahan said. So what do you also recognize? You think of these 10 simulations here.
It's not that much statistics, but there are 4 out of 10 equals around.
Okay, so we shouldn't.
They're very different.
They're very different, right? So there is not much of a statistics here, that's true. If you would do this for 1,000 simulation, everything would be black here. So that means this process has no preferred stationary value, right? So in fact, you can prove mathematically that every single value of these x's is possible. You can get any number. That's the second important thing. So you log in to something, yeah? But it's completely unclear and completely unpredictable for the linear process which x you choose at the end. That is the important message. You can be logged in into any state, right? Is it good or bad? What do you think? Yeah. That's correct, yes. That's bad. If we want to predict something, then we better know what the outcome should be. And so that's true.
But it's good in the sense that there's no bias in the beginning, so we can reach every state.
Right. So that means there is basically an open evolution. Right. So this gives us our number of possibilities. Right. So we cannot predict the system. But we have ample of choices. Well, you can see it from both ways. If we have just one value to convert, right? So then we are just talking about the time at which we log in. So, okay. These are the two important messages. I can skip this slide because we just talked about this, right? So, it converges to a path-dependent equilibrium. What value we have at the very end depends on the sequence of how we got there. And every new addition to the urn generates a smaller, and smaller impact. Yeah? That is the message of this slide here. So, okay. We can also skip this slide because we already discussed this. In the beginning, you have a chance to invert a process, right? That's the first step after the initial condition. The initial condition was 1 black, 1 white, right? So now we have chosen accidentally a black. So then we have 2 black, 1 white. So that means the blacks are dominating. What is the probability that we can, at this is step number 2, right? That we can invert starting from step number 2, that we can invert the situation where the blacks are the majority. We want to have the white as a majority. We can think about this. So first, we have to choose more white, right? So in the beginning, so the probability that I choose one white is 1/3, because the blacks are dominating. Yeah? 2/3 versus 1/3, 1/3. So then I have 2 whites, 2 black. The probability to choose one white is 50-50. 2 white, 2 black. So then I have the whites dominate. And then the probability to choose again one white is then 3/5. So, and if you multiply this, because we are talking about independent effects, then the probability to invert a state like this, which is right one step after starting with the game, is only 1/10. That's very small. That means 90% of the probability reinforce the given initial fluctuation. And only 10% is the probability to invert this. No? So you see it's almost impossible. But if you then go for larger numbers, so then you see it's literally not happening anymore. Okay. So now we come to the nonlinear polar process. Here the assumption in the linear process, if you have to describe this in the exam, then the assumption is that the probability to choose a black or a white stone is proportional to the percentage or the frequency of the black or the white stones in the urn, right? So that means there's a linear dependence. P equals or proportional to x, and x is a fraction of these balls. Right? So what you can think, if you want to do an application, you can think of all other possibilities here. So you can say, okay, the proportion of choosing the probability of choosing a black stone is just decreasing with the number of black stones. So it's proportional to the number of white stones, for example. Then you would get something like this, which is here called minority voting. Yeah? Or you could say, okay, I choose a black stone if the proportion is below 0.5, and if it is above 0.5, I choose a white. Right? So that's, you have ample possibilities of setting this relation between what you see in the system and what is the probability of doing the next step. So, and that's called nonlinear polar process. And choosing any form of this proportionality results in a considerable difference. The linear polar process, what is this? Yeah? The probability of adding a black stone is directly proportional to the existence number of frequency of black stones here. And then we remember from this picture that we have discussed that every outcome is possible. Yeah? So, yeah? That means the ball can be here, but also there. So there is no preferred state. But if I choose any of the linear functions, then this linear, any of these dependencies in a nonlinear way, I'm talking about this kappa here, yeah? Which is, by the way, the ETH there, no? Alex? Yeah? So, okay. Then this picture changes. So if we have something that's more than proportional, for example, then we have a banded shape like this. If it is more than 50%, then the probability to changes is increasing. If it is less than 50%, the probability of choosing the black stone is more than proportionally decreasing. So if we have something like this as a dependency, then we end up with only 2 equilibrium states here, namely 0 or 1. So that means instead of having a million possible outcomes, we only have 2 possible outcomes. So if you want to predict the system, as Farhan said, then you are much better in tuning the mechanism at which the process is amplified, right? That's what you basically do. You choose a non-linearity that's in favor of you. Yeah? You are the company A, and you have invented the whatever phone, the A phone. And now you want the market to log in your phone. You want to be here, right? Then you choose an amplification that is not just proportional to the number of people using the A phone, but gives you additional incentives. For example, you reduce the price proportional to the number of people using the phone already, right? So that's a nonlinear feedback that increases it. Or you say for every 10th customer buying the A phone, I give a set of the A tablet for free or something like this, or for every 50s or something like this. So you think about ways of twisting this probability in favor of you, and then the nonlinear voter model will predict that you end up always there, right? This is, of course, not realistic, but this is what companies are doing. So they try to choose a nonlinearity that allows a super linear, more than linear amplification of the choice of the customer. That's, by the way, the same as whatever Microsoft does. And they say, well, we have this nice browser, and if you buy the whatever suite for office work, then you get the browser for free, right? So that's the idea, okay? Where the conflict with the European Commission came from and these kind of things. You understand that you as a company have a possibility to change this outcome in favor of you. But you should be aware that all the other competing companies try to do the same, right? So we talk about the limitation afterwards. So what you get then is a much, much stronger lock-in effect, as you can see here. Why do I say it's much stronger? Because they do not only log in, they also log in either of the states. So instead of having any possible outcome, they have only two possible outcomes. That's why I say it's a stronger lock-in effect. I hope you got the point, right? So, are there examples of lock-in effects? So, the famous example discussed in the literature, I will be very short, is the QWERTY keyboard. I assume everyone knows what the QWERTY keyboard is. So, people found out that this is a suboptimal way of writing. There are other keyboards now, keyboards like Microsoft Natural Keyboard or kind of this. This never materialized. So even this small iPhone now, so where you don't have a keyboard anymore, this imitates the QWERTY keyboard. The question is, why is this like this? That's an early amplification. The QWERTY keyboard was chosen at a time where you had typewriters. Do you still know what a typewriter is? So, okay, typewriter is something that you press A and then a little, how do you call it? This, yeah, something. How do you call it? Lever. A lever comes and hits the paper, right? So, okay, and then there is the A. And the keyboard was chosen in a way that there is no conflict between these letters moving forward and backwards, right? So people thought about what is the minimal conflict, So they thought about what is a natural sequence of letters in a word, and then of course they made sure that these letters that naturally appear one after the other are not on the same place of the keyboard, because then you had a limited speed of typing, because you have to wait for the letter to move forwards, make click, move backward, and then the next comes, right? So that was the optimization criteria. It made perfect sense at that time. But in the age of a computer, you could have chosen anything, right? But that's a very strong re-amplification effect. So, and because all these people were trained like this, and there were education books and courses to train people like this. So this was amplified again. So without any rational other than this early one. And there are thousands of examples for this. No? Okay. Now let us come to the last 5 minutes to discuss a small model which is a bit more realistic, but the message is not different from what we just discussed. Now we have 2 different kind of agents here. The assumption before was that every agent is similar, no? And then gets randomly assigned black or white, right? So with a certain frequency. But there was no personal preference of the agent. The agent was not asked, do you prefer to be black or white, right? So this was not the case. But now we have exactly this assumption here. We have the R agent and the S agent. You think of black and white again, and the R agent has a preference for the product A and a preference for another product B. And for the S agents, these preferences are differently. So precisely, I think it's written here, the R agent prefers to have product A, and the S agent prefers to have product B. Right? For natural reasons. You know? You understand? That is it. So that means if I let the system run and have no other effects, then I would find a distribution at the end which shows me A products and B products according to the frequency of R agents and S agents. You understand? Because the R agent prefers the A product and the S agent prefers the B product. So that would be the outcome of this. That means I could, from the outset, completely predict how the distribution of the 2 products, A and B, would look like. So that's described here. So, but now we have another assumption, say, in addition to having a personal preference, just for the moment, yeah? So let's talk about the Apple iPhone and the Samsung iPhone, right? So that's something we could choose, yeah? So just to give you an idea. So these are the Apple fans and these are the Samsung fans. The share is about equal, yeah? Now we have an additional feedback. The agent has not just his own preference. His choice also depends on how many other agents in his environment have chosen the Apple product or the Samsung product. So, and here you see, so this agent has a preference for the Apple product, but you can see if very many people in his environment have chosen product B, which is the Samsung phone, then of course the utility he gets from also choosing a Samsung phone is larger at some point than the utility from choosing an Apple phone. Why is this? Not because of his preference, but because so many others did this choice. And then he can no longer talk about the iPhone store. He has to talk about the Google App Store or something like this, right? So there is a point of choosing what the other people have chosen because it eases communication and you have always something to talk about, right? Even in our group, so then we talk about our Android products, right? So, okay. So it's very clear if you do not have any preference and you see, if you do not have any enhancements, then you see a distribution according to the initial preferences, how you are born and enter the system. But the important thing, so that's then what you get here. Yeah? The equilibrium is 0.5, and then any randomly chosen sequence of either Apple agents or Samsung agents changes this equilibrium towards this random number. But it converges basically to 0.5. So now the difference is I do not just look into my preference, I also look into what did the other people choose. So, and then I have to compare these utilities. So for agent, for the R agent wanted to choose the Apple product, right? Here. So this AR is larger than the BR that was written 2 slides before. That's the Samsung product. But because more people have chosen the Samsung product, so this utility is larger than this utility. And then you can calculate a difference here, NA minus NB. And if this difference is below a certain threshold here, which we call delta R here, then the R agent, which is the one who prefers the Apple product, will choose the Samsung product, even that he has a natural preference for the Apple product. And you can do the other way around. You can calculate a difference at which the preference, the number of people using Apple product is so large that an agent who naturally prefers to buy a Samsung product and has a larger utility from buying a Samsung product because of his preference will eventually choose, let me just finish with this, will eventually choose something, choose the Apple product, right? So. And this is the slide at which I want to stop, actually. You see, in the beginning, we have this kind of random walk process between R and S dominance. R means Apple product, B means Samsung product. So, but you see, when this delta S or delta R are hit, these are the two boundaries. That means there is a critical number of agents choosing Apple or critical number of agents choosing Samsung. Then the others log in. Once they logged in, there's no way of leaving the state anymore. Because then you can only, after this point, you can only amplify the Samsung or the Apple state, right? That means in the beginning you have a bias because of the preferences, but then it really depends on the sequence how agents enter the market and how many other agents are there, and then you see either something ending up here or something ending up there, right? So that's again a polar process, as we have seen. So it's a linear polar process because we have this proportionality with the number of agents. But at the same time, it's not a perfectly linear process because we have these preferences added. The agents start with the bias, right? So you can also say it's a non-linear process, but in a rather complicated manner, right? So and therefore, we have this log-in into either of these states. This is because of the preferences. If we drop the preferences, you can test this when you do your little exercise at home. We drop the preferences, then we are back at the linear polar process, where everything is just proportional to the number of choosing Apple and Samsung, right? So that means here we have a combination. There is this amplification effect, but there is an initial bias. So essentially, the possibility of equal states at the end, you could choose everything. This is broken down in favor of log-in either in A and B. Of course, this process is not really realistic. Therefore, on this slide, we discuss a few limitations of this. I want you to read the slide at home. It is important to understand that even this picture does not capture a full model of technology adoption, because there can be other companies entering the market. There can be ample ways of influencing your preferences. I just lower the price. Maybe you change your preference or these kind of things. Or I have a mobile vendor behind this, like Sunrise versus Swisscom, and then you also choose according to what Sunrise or Swisscom are offering in terms of hardware, right? And all these kind of things. So it's important to understand that this is a caricature of an adoption process, but at the same time, it's not a complete model of describing interaction in the market. That's important to understand. So with this, we stop. Next week, we don't meet because there is a holiday, and we meet in 2 weeks again. Yeah? So I will send you an email in the meantime, because this week, the week when we meet again is the last week, as far as I understood, right? Or no, it's the 20th. No, we have the 24th, and yeah, we have two lectures there. Okay. Okay. Thank you very much. So, good morning, everyone. I welcome you to lecture number 11 of our course, Collective Dynamics of Firms. As I mentioned in the email, today we have the course evaluation. I assume that there is not a very good statistics from 6 students here, but nevertheless, we would like to distribute these sheets. If some of you attend the exercise and haven't done this yet, and you can also do it together with Pavlin. Yeah? Maybe you can distribute this here. You return this during the break, right? I think that everyone is familiar with this, right? Or is there a question? The course number, yes, you are right. What is the course number? I write it down here. The course number is 363053. So that's the course number, yes. So you do not need to rush with this. You have time until the break. And in the meantime, I will entertain you with some slides. Right? Okay, so where are we in the course right now? We looked first into data, then we found some stylized facts about the size distribution of firms and the growth rate distribution of firms. And then for the rest of the course, we tried to develop agent-based models to reproduce the stylized fact. So the surprising finding was that you were able to reproduce these stylized facts already from very simple assumption that from the outset have not a real economic interpretation, right? If you think about the stochastic growth factors, so then it's impressive that you get the distributions without assuming anything about economics. Therefore, in the second part of the course, we try to enhance these agent-based models step by step. So the first step that we did was considering indirect competition or indirect interaction. How did we do this? We considered competition in a market, in a kind of free market capitalism. And then we found that because of the competition, some of the firms will survive and most of them not. So this is a nice intermediate result, but it doesn't reflect the state of an economy where we have small and big firms coexisting. So that means in the next step, we try to add assumptions about interaction that results in coexistence of firms. And we did this by 2 different models. One was the redistribution of wealth, which had an impact on the inequality distribution. And the other interaction assumption was cooperation by exchanging knowledge. This was done in the last course, right? So you learned how firms depend on the input of other firms. There was a baseline model, and then to this baseline model, we step by step added assumption about utility maximization. So the question now is, do we cover the economy or the dynamics of firms by just considering utility maximization? So the answer is not, as we will see today, because only in rare cases you can really calculate utilities, right? Of course, if you think of the problem from the perspective of the firm, then there is a strategic decision with whom to interact and so on, right? But this is usually not really made based on a calculation of a utility. There are also social effects that are included in this decision. What we do today is we entirely, in the first part, focus on the social processes. So you as a firm, you decide to do something not because you are convinced to do this, but because you observe that all others are doing it, right? So there are herding effects, there are social influences, yeah? So you observe what other big players in the market are doing, and then you try to adopt their behavior because you can observe that these are successful firms. You do not know precisely why they are so successful. You can just observe they are successful, and then you try to copy their business strategy, for example, yeah, their production layout or whatever, right? So that is the focus of today's lecture. So we will talk specifically about herding effects in firms, that firms try to imitate other firms. And we will also look into so-called lock-in effects, which means what happens if you copy the decisions of other firms or the policy of other firms. How does it lead to states that are hard to change? That's behind this path dependence and lock-in effect. So with this, we have a number of slides today. I'm not going to read all of these. I try to be a bit short. So this slide should motivate why we are interested in this. The best thing is I'm not going to talk about this famous paper by Allison and Glaser from 1997. We have put this in the literature folder. If you're interested, you can take a look into this. I'll just address the basic problem. So if you look into the spatial distribution of firms, then you see that there are clusters of firms that emerge in certain areas. The best known example and the most copied one is the Silicon Valley, right? So there were a number of small firms that have been established either as spin-offs of Stanford University or because of some local connection with the industry. And then this started to grow and became a very prosperous area. So the question is, how did it happen? So everyone wants to have a Silicon Valley in his canton or in his country, right? So everyone wants to have this. So the question is, how did it happen? What is behind this success? And people try to understand this because if you go there and look, then you see that the firms in these local clusters have similar business culture, right? There is this saying or rumor that they never had written contracts. Everything was agreed on in the pub or in the coffee shop and these kind of things. Yeah? So, of course, that's wrong. The assumption is instead of explaining this from a utility maximization, we assume that firms locally influence each other. So you see what your neighbor is doing, and then you behave in a similar way, or you adjust your behavior in a way that you can better collaborate with your neighboring firm and these kinds of ideas. Right? So here we have listed two classes of modeling, the voter model and the bounded confidence model. So the voter model is not captured in this lecture, actually, but I should mention it. A voter model is a very simple model. You assume that an agent is characterized by one of two states, 0 or 1. This can stand for anything, right? Let's assume it's an opinion or something. And then this agent can adopt this state according to the number of other agents in the neighborhood that have the same or a different opinion or state, right? So that means the agent is in state 0, and then the agent looks around and sees he's surrounded by all firms in state 1. So, and then the probability that the agent switches towards state 1 becomes very high. or the other way around, and so on, right? So that's a voter model. First of all, it's a binary variable, -1, +1, something like this. And secondly, it's a frequency-based model. You calculate the frequency, the percentage of agents in your system, your neighborhood, and then you adjust your decision according to what all the others are doing, or different from what all the others are doing. That's also possible. Yeah? If you see everyone is in state 1, then you think it could be beneficial to be in state 0, right? And have a different business model, for example. So that's the idea. So these models, these voter models, are well studied in various scientific disciplines, notably in mathematics, but also in physics. I'm not going to talk about this. I could, because I did some work myself in this direction, but that's not important today. Maybe the important thing that you should consider is the voter is not voting, right? But it gives you a kind of flavor of what people think was the culture in these early days when Google was founded, or Apple, or something like this, right? So that's the idea. Okay. And we would like to understand how firms influence each other in creating this local culture. Because essentially, the existence of such a local culture is an important ingredient for the establishment or the survival of something like Silicon Valley. I should mention that Silicon Valley is just one example here, though. We have another example in the Boston area, which is also well studied in the literature. Boston 128, that's a route out of Boston in the south, where firms locate and aggregate. So, and people want to understand why is it like this. So, the modeling has to start with an agent-based framework. That means so we are not looking into density functions of how firms are distributed. We look into the problem of aggregation from the perspective of a single agent. So it is also important that we do not enforce the result, namely the emergence of a cluster and a local culture, by putting this in somehow in the model. Yeah? There are some people that are really smart in tweaking the model exactly the way they want to get the result, of course. Yeah? So here it's important to have not a central authority that basically governs the interaction behavior of this firm. Instead, it has to come up as an emerging property, as we name it in complex systems science. And the third important assumption that is listed here is we do not assume that firms get into the state based on utility calculation. Why not? First of all, we do not know the utility. We want to do it in a utility-based model, then for the rest of the lecture we just talk of how should the utility look like. And then, of course, we have to go and have to test these assumptions with an econometric model and so on and so on and so on. You know these from other courses, right? Here our